Assalamualaikum everyone. My name is Nur Izzatiana binti Hashim and my partner's name Nur Nazira Hanis binti Nazri, and we are both from section 2 for computer organization and architecture for Miss Rashida's class, and today we'll be demonstrating on the debugging part or the debugging process for our lab 1. So for today, I'll be explaining on the debugging process for the first part, which is for part B, and my partner will explain on the later part. So now I will demonstrate the debugging process for part B, which is for adding variables. So first, I will start my program by putting it in debugging mode by pressing the F10 button. So this can allows me to execute the program step by step. And next, I will open several important debugging windows, which are the wash window, registers window, memory window, autos window, and the last one is the disassembly window. So these tools can help me observe how the program will behave internally. Okay, so next at the wash window, I will add the variables that I have in the code into the wash window. So the variables are the val1, val2, val3, and the final val. Okay, so initially the values for all those variables for val1 it is equal to 10,000 hexadecimal, val2 is equal to 40,000, and val3 is equal to 20,000, as you can see in the wash window where you can see the initial values. So for the first step is to move val1 to EAX. So at this step, the value of val1 will be moved to the EAX register. So now EAX will be equal to 10,000 in hexadecimal. So as you can see in the register window that EAX is now changed to 10,000, and at the wash window, the val1 remains unchanged because we did not do anything to val1. And as for the memory window, it's showing that the val1 is now stored in the memory, and at the disassembly window, it is now highlighting the current instruction. So for the next step is to add val2 to EAX. So here the value of val2 will be added to the EAX. So now EAX, which previously are equal to 10,000, will be added to 40,000, which is the value for val2, and now we can get the value of EAX, which is equal to 50,000 in hexadecimal. So you can see at the register window that the EAX has now been updated to 50,000 H or hexadecimal, and at the wash window you can see that the val2 is unchanged because we did not do anything to val2, and at the outers window it is now showing the intermediate values. The next step or for step 3 is to sub val3 from EAX. So now the value of EAX will be subtracted with the value of val3. So EAX, which is previously equal to 50,000, will be subtracted with 20,000, which is the value for val3, and then you will get a final value equal to 30,000. So you can see at the register window, the EAX has now become 30,000. And at the wash window, the val3 remains unchanged because we did not do anything on the val3. Okay. The last step or the fourth step is to move EAX to final val. So the final val in EAX will now be stored into the variable of final val. So you can get the final val value will be equal to EAX value, which is equal to 30,000 in hexadecimal. So you can see now at the wash window, the final val is now updated to 30,000, and at the memory window you can see what the new stored value is. We have now completed the debugging process for part B, and throughout the process, I observe how the register window shows how the EAX value changed step by step, and at the wash window, it can shows me how the variable is updated, while the memory window shows where the values are stored, and at the disassembly window, it shows me which instruction is currently being executed. So in conclusion for part B can demonstrate how the variables are loaded into registers, how arithmetic operations are performed, and how results are stored back into the memory. So debugging allows me to track every step and verify correctness. So that's all for part B, and that's my partner will explain on for part C. Thank you.
Okay, now I will demonstrate part C, which is involve operation using 18-bit and 8-bit data. This part shows how different register size for during execution. The program is executed in debug mode using F10, allowing step-by-step observation. Several debugging windows are open, include register, auto, wash, memory, and the assembly. These to monitor the program behavior. Now, let's take a look at the wash. We can see here there is wall 1, wall W1, wall W2, wall W3, final wall W, wall B1, wall B2, wall B3, and final wall B. And this value is the value for all of these variables. And as you can see, this value will be stored in memory before the execution. And this is the address for all of these variables. Okay, for the first step, you see move as wall W1. At this stage, the instruction has not yet been executed. So the X register will contain an initialized or previous value which may appear a random hexadecimal value. So here you can see at auto the value is a random value, not 1000 yet. So when it is executed, as you can see here, it's moved to X or W1. So the first instruction will be executed. Here, the value of AX will be updated to 1000. And also at assembly, it will show that the value of AX is 1000. So for the AX or W2, it also the same. It is not executed yet. So that's why the value is still 1000. So when we overstep again, so now we can see that the X value is 5000. Why? Because the first value, which is 1000, is added by 4000, so it's get 5000. This is based on the instruction given. Move that. Now when we start over again, then we show that the X value is 3000. And here also show that the AX value is 3000. Yes, the previous 5000 value is then subtract with 2000. So we can see it is the instruction of sub AX value B3. This value B3 is 2000. So when we overstep again, as you can see at the watch and to memory, the value for final wall V will be updated to 3000. So the X value will store 3000. Then for the 8-bit operation, first we can see that there is wall B1, wall B2, wall B3, and final wall B. Here is the value for all of this. And also at the memory, the value will store here. Now, just like the previous for the 16-bit, we can say that here there is AH and the value is 550 because just like before, the value is not, the instruction is not executed yet. So it return the previous value from the AX. Since the AX is 3000, so the AH will be 30. While the AL is 00. Since we only have one AH here, so that's why we get 30. So when we overstep again, now the AH value is 10. Why? Because it is the previous instruction which is move AH wall B1, where B1 value is 10. So that's why the AH now is 10. And when we step over again, the error will move 10. The previous instruction will also be executed. So now the AH will be at with 40. By 40 because the wall B2 value is 40. So we will add 40. Now the AH value is 50. Then first step again. Now the AH value is 30. Why? Because the previous instruction is sub AH wall B3, which means that the AH value will be subtract the value of wall B3, which is 20. So that's why AH now become 30. Now, when we first start again, it will call down register. So now that the final value for final wall B is 30, and the memory part will also be updated, showing that the final wall B is also 30, and here at auto we can say that the final value for AH is 30. As a conclusion, we can say that from this demonstration, AS value is used as a 16-bit register for word operation, while AH value is used as 8-bit register for the AS part. So the register value will change step by step during the execution. So you can say that 18-bit and 8-bit operation are processed differently. The stuff is transferred into memory and register, divided into allow real-time observation of the program execution. So that's all from me. Bye.